All right, so here we're going to be talking about our electromagnetic radiation on pages 18 and 19. 19 is really when we're going to focus on those light calculations. This is the last big idea that's going to be on your Unit 2 test. So let's get started. Electromagnetic radiation is really kind of just a fancy word for light. And so the visible light that we see is electromagnetic radiation, but it really is only a very small part of this overall spectrum of different types of electromagnetic radiation. In fact, that visible light that we call light is just this really tiny portion here in the middle. So really, when it comes down to it, electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. So that's a more generalized definition that can apply to all of these different forms of electromagnetic radiation. And we're going to be talking a lot about these words that you see at either end of the spectrum, the wavelength, frequency, and energy of this light. And while you don't have to memorize these relationships, what you should kind of start to realize, and it can help you be more confident in your calculations, and this all kind of comes back to this wave you see down here below. The shorter the wavelength, meaning the closer together our waves are, the higher the frequency is, meaning the more frequently we have a wave there in that space, in the same amount of space. I have more waves more frequently over here than I do over here at this end with our longer wavelength, the longer distance between waves. And if you imagine that this wave is a string, maybe tied to a doorknob that you're shaking up and down to make this wave, then you could understand how this end with the more frequent waves, so the shorter wavelength, you'd have to put more energy into shaking that string to produce those waves. These waves down here with the longer wavelength are lower energy. You can kind of shake that string a little bit slower and with less energy to get those same waves. So these kind of numbers and properties are going to be things that we're comparing in numbers, really, in those calculations. But you can see those relationships here on the spectrum, and that applies to all of these different types of light. So we can say that gamma radiation has a shorter wavelength than micro radiation. And even in here in the visible spectrum, if you maybe write down the colors, this is kind of the backwards rainbow, Roy, G, Biv. So violet light would have a shorter wavelength than yellow light or red light, and red light has the longest wavelength of any of that visible light. So we can use this spectrum to make those generalized comparisons. Now, what we're going to really be focused on more is, there are those little notes popping up, is how this light is produced from atoms, and kind of more specifically into Bohr's flame test that helped us understand the energy levels of the atom. So we're going to talk a lot more about that hydrogen emission spectra that Bohr was studying. And a hydrogen emission spectra is some lines of color produced when the electrons, specifically if it's a hydrogen emission spectrum, the electrons in a hydrogen atom are excited. And those electrons are going to jump up and get excited and then fall back down to their ground state. And that's how that emission spectra is created. But a couple of words there you need to understand. Ground state is kind of where the electrons should be when we're writing those electron configurations. That's their ground state. The excited state is a very temporary position, but they can jump up. When we get them excited, if we give them some energy, those electrons can jump up to a higher energy level. And so that's what we call that excited state. But what goes up must come down. So when it comes down, it releases that excess energy we gave it as light. Think of it like on a roller coaster. They put a lot of energy to getting you to the top of that hill, and when they release you, it's when you're falling down that you release all of your pent-up energy in probably a little bit of a scream and your excitement there. So if we look a little closer at these spectra, hydrogen emission spectra is not a continuous spectra. It doesn't have a continuous rainbow color from one end to the other with all of the spaces filled in, every single possible variation of that color. A line spectra is going to be separate lines of light, and we might have different colors in those separate lines, but they're not continuous. I don't have every single possible shade of red, orange, yellow, green, blue, and violet. And those specific lines of color come from these specific energy levels in our atom. So in this area, you have this little kind of section of energy levels off to the side. That just kind of reminds you that if we had our nucleus of our atom kind of here, that first energy level would be pretty close to that nucleus. And then there'd be a gap, and then there's a second energy level. And we kind of drew these. Well, we didn't draw these, but if you're kind of imagining a Bohr diagram, this is just kind of a small section of that diagram that ends up looking kind of like a ladder. And each line in that emission spectra we just saw is produced by the emission of photons of certain energies. And they have very specific certain energies there that is equal to the difference between the ground state that that electron started on and the excited state that it jumped to. And these little lines that we have over here are trying to kind of show that. So if we have an electron in the ground state, the lowest possible state, and then it jumps to the excited state, where the electron is a higher energy level than it should be. It's unstable, which means that that energy that we put into it is only going to hold it there for a moment. Then it's going to fall down, and it's going to release either the exact same amount of energy it absorbed if it falls right back down to that ground state, or there can be some times where it just falls a little bit of the way the first step and then a little bit more. So sometimes we can have more than one different amount of energy released, even for the same amount of energy put in, which is why we can end up with multiple lines in our emission spectrum. But still, the amount of energy is quantized. We can't have an electron fall down or release kind of 1.5 energy levels. We can't just stop here. It would have to fall all the way down to that second energy level or all the way down to the first. It can't stop in between. So because the position of the electron is limited, the colors that it's creating are limited. And that's kind of the question we're answering at the top of page 19 here. Why do we produce unique line spectra instead of a continuous spectra? Because those electrons have specific orbits at specific energy levels, and they can only move between those specific levels. The electrons can only absorb and release specific energies of light, which means we create specific lines with specific energies, not every possible color and not every possible energy. So that's kind of a little more in-depth view of the theory behind Bohr's flame test. I know we talked about it a little bit at the beginning of the unit, but that's really important you understand how those energy levels were discovered. This is a really important scientist for chemists. Okay, so what we're going to spend the rest of page 19 focusing on are these calculations and these two different equations and some example problems that go with them. So the first equation I've highlighted in green for you here, C equals F lambda. Lambda is that weird upside down Y looking symbol there, and each of those letters represents one of the fundamental characteristics of our waves. So C is the speed of light, F is frequency, and that weird upside down Y, lambda letter, represents wavelength. You can kind of see that in the word equation that is right underneath the symbol equation, but I'd like to make sure that you write down the correct units that go with each of those measurements. So I think off to the side is where it fits best. Speed of light is in meters per second. Frequency can be either hertz, which is Hz, or inverse seconds, 1/seconds. Technically, that's what hertz represents. They are equivalent, so it doesn't matter which one you use. And then our wavelength is in meters. Now, that speed of light number is always the same number. It's always 3.00 times 10 to the 8th. So we're not really going to be solving for that. You're probably never going to have to put those units on any answer. And in your calculator, when you get to class, I'm going to show you how you can plug in these scientific notation numbers to substitute that times 10 raised to a power with an E. And that's going to make all of our calculations actually turn out a lot more better. When we're doing math with scientific notation, it helps our calculator understand that that's one number and not a math problem that we're doing, because a lot of calculators are going to do the wrong order of operations with these scientific notation numbers if we're not careful. So I'll show that to you in class, how to push the buttons to get that E in our calculator, but you're going to see it pop up a couple of times here in our notes. And if you don't have one of my calculators at home, it might be a little bit hard to get it there. So another thing that I'm going to want to make a note on while we're talking about units is that wavelength is, the standard measurement is in meters, but there's a chance you might be given nanometers because the light that we're working with is so tiny that that's the common measurement to measure that length in. So if you're given nanometers, we need to turn it into meters before we plug it into our equation. And so the quick and easy way to do it, instead of setting up and working out a dimensional analysis problem, is just slap an E-9 onto that number. Like if I was given 350 nanometers, then 350 E-9 is how many meters that would be. Now, technically, scientific notation wouldn't be in the quite right format with the decimal in a different place, but that value is the correct value, and that can let you get your calculations done quickly and easily without getting distracted with some dimensional analysis. So that equation, like I said, C is a constant. It's always that 3.00 times 10 to the 8th. So this equation, solving for C, is not going to be very useful to us. Most of the time, you're going to need to rearrange that equation in order to solve for either your frequency or your wavelength. And the good thing is you can solve for either of them in one step. Whichever one you're solving for, you'd need to divide by the other. So if I'm looking for F, I'd have to divide by that lambda on both sides to get F on its own, which means F is equal to C divided by lambda. But if I wanted to solve for that lambda, that wavelength, I could divide by F instead, and wavelength is equal to C divided by F. So, pretty simple to rearrange equation, but you're always going to have to rearrange this one to use it. I'm going to give it to you in that standard form, and it's highlighted in green, but you're going to have to rearrange it in order to plug in those numbers. So, let's do an example. Here, this is asking us what's the frequency of green light that has a wavelength of 4.9 times 10 to the negative 7 meters. Reading through that problem, what I'm given is a wavelength, so that's going to be that lambda letter, and we're looking for a frequency, so we're looking for F. So I want an equation for F that has that lambda in it, and that's going to be our C equals F lambda. Remember, we are going to have a different equation, so sometimes we are going to have to make a different choice on which equation to use. And I'm going to use the rearranged version of that equation that's going to help me solve for F. So I just need to plug in my C value divided by that lambda value. So 3.00 times 10 to the 8th divided by 4.9 times 10 to the negative 7, with those e's instead of the 10s. Plugging that into our calculator, we would get out 6.122449 times 10 to the 14th, which we would round to 3 sig figs, just keeping the first 3 digits of that base there, gets us 6.12 times 10 to the 14th. And remember, since this was a frequency, we put hertz there as our unit. You might not have a calculator that you can plug these in on, so make sure you just write down these problems, and as soon as you get to class, you can double check and make sure you know how to put these in the calculator correctly and that you can get the same answers that I am. So in this next problem, it's asking us to find the wavelength of light that has a frequency of 8.50 times 10 to the 12th hertz. So our given here is frequency, and we're looking for the wavelength. Remember, that's that weird upside down Y symbol. So we need our equation with frequency and wavelength in it. It's the only equation we have so far, but we're going to rearrange it to solve for wavelength. So we're dividing by that frequency on both sides to get wavelength by itself. So wavelength equals our C value divided by that F value in the problem. So we plug in that same exact C value, 3.00 times 10 to the 8th, or 3.00 E8 in our calculator, divided by that 8.50 E12 that was given to us in the problem. And when we do that, this answer comes out of our calculator. We'd round that to 3 sig figs because our given had 3 sig figs. So just changing that base, 3.53 times 10 to the negative 5 is our final answer. Keep in mind, because that was wavelength, we need meters on that to be our full and correct final answer. So even though these numbers are kind of big and they look a little bit weird, once we get our calculators in front of us and start learning how to push that E button, it's really pretty simple. So we have one more equation that we're going to be using, and it's also pretty simple. This one is actually about the behavior of light as a particle, and it can act like a wave and a particle, which is kind of a weird thing for, matter in general or energy to be both, but we don't need to worry about those quantum mechanic things. Just focus on this equation. E is our energy, H is our Planck's constant, and F is frequency. And that Planck's constant, that H, we would also write out with an E in it in our calculator, but that's a constant, kind of like the C value in the last equation. It's always going to be given to you. It's always that number in our equation. So because we know what H is, this equation is set up to help us calculate energy. We just need to multiply H times whatever our frequency is. But sometimes we might need to use it to solve for frequency. So these are the units that go with all of those numbers. You've seen those joules before in our Unit 1 test, but you didn't really know what that J meant back then necessarily. So now it is our unit for energy, so just a J at the end of any energy numbers, and frequency is still hertz or inverse seconds there. But we might need to rearrange this equation to solve for frequency. And to do that, we'd have to get rid of the H that's over on that same side with our F. So E divided by H is our equation for frequency. So we're just going to work two more quick examples. And that first example is giving us the frequency and asking us for energy. So we have an equation that has energy and frequency in it. So that's the equation we're going to use. And really all we got to do is plug in that H value times our F value. Learning how to put these E's into our calculator, we would get this answer out as an unrounded answer, and we would round that to 3 significant figures in order to make it match our given. So that would end up being 4.19 times 10 to the negative 13th. And because this is energy, that would get a J on it for our joules, and then we're done. This last problem is a little trickier than it might seem. We are trying to calculate energy here, but it gave us a wavelength, not a frequency. And we don't have an equation that has energy and wavelength in it. So this type of problem is the hardest type of problem because we kind of have to use both of the equations that we have on this page working together to do this. Because we have an equation for energy, if we have frequency, we can use the wavelength equation to solve for frequency and then plug that in to our red E equation. And you can do that mathematically in separate steps, or we can actually do that with these equations right now. We've already rearranged that green equation before to solve for frequency. If we plug in that C over lambda into our red equation here for that F, then what we get is this new purple equation that we don't have to do any fancy rearranging once we get those big complicated numbers into them. Now, this equation isn't given to you in the page, but you can use this anytime you've got a problem like this where we're trying to calculate energy and we're given wavelength. And it can save you from having to do as much algebra with the rest of your numbers. Because here we can see all we really have to do to find energy is take our H value times our C value and then divide it by that wavelength number. And if we do that, plug it into our calculator carefully with those E's, we'd get out 2.31 times 10 to the negative 19th. And that would also, of course, have those joules units on there. So I know that right now you're kind of writing down a lot of math and you're not able to put it into your calculator necessarily, because even if you have one of my calculators, you might not know exactly where that E button is. You could look it up online, but I will spend the first 5-10 minutes of class just making sure you can find those buttons. That's not something I need you to be able to do walking in the door, but hopefully you can understand the general algebra and process for solving for these values with these simple equations. It's just going to give us some complicated numbers, but once we learn how to plug them in with these E's, all of the math should be pretty simple and straightforward. So come to class with questions if you got them, and I promise I'll teach you how to use the calculator to make these calculations simple.